I'm from Southeast University, which is located in Nanjing, Jiangsu, China. I will present our stories on behalf of our team. The theme of this presentation is an analytical loss model for magnetic cores based on vector magnetic circular theory. Before I begin, please allow me to briefly introduce our team. Our team has two instructors. One is Professor Ming Cheng. He is a chief professor and the doctoral supervisor of Southeast University. Part of his resume is as follows. The other one is Professor Zheng Wang. He is also the professor and the doctoral supervisor of Southeast University. Part of his resume is as follows. According to the organizer's requirements, our team includes 4 student members at different stages, including undergraduate, master's, and doctoral degrees. Cut to the chase. This presentation is divided into 4 sections. The first section is introduction. Accurately predicting magnetic core losses is crucial to achieving optimal design of magnetic components. Currently, there are 3 main methods used to calculate core losses. Among them, the Stamets equation-based methods for core loss has been favored by engineers due to its practical quality and simplicity. The picture on the right is from a webinar hosted by the organizer. It can be seen that the existing model cannot achieve satisfactory results in both dimensions of accuracy and complexity. The existing Stamets equation based methods only cares about the total loss of the magnetic core and doesn't study eddy current loss and hysteresis loss separately. In order to explain the source of loss more based on physical phenomena, our research group proposed a vector magnetic circular theory. We hope to calculate the core loss from another angle and use as small a model as possible to obtain as much accuracy as possible. The existing magnetic circuit has only reluctance component, which makes it impossible to analyze the hysteresis loss and the eddy current loss. Based on this situation, our research group proposed a vector magnetic circular theory, which represents the core loss through magneticness and hysteresis components. In the second section, I will briefly introduce the vector magnetic circular theory. The reluctance expressed by R is consistent with traditional scalar magnetic circular theory. The equation of R is as follows. Based on the obstructing effect of a closed conductive coil and the hysteresis effect in magnetic materials on the alternating magnetic flux, the equation of magneticness and hysteresis is as follows. When the magnetic circuit is excited by a steady-state sinusoidal magnetomotive force, the following steady-state expression can be obtained using the Fisher method. Combined with the magnetoelectric power law, the magneticness and hysteresis are related to losses. The active power is generated by the magneticness and hysteresis. Meanwhile, the reactive power is generated by the reluctance. In actual situations, the shapes of magnetic cores are diverse. Here we use a rectangular cross-section magnetic core as a standard. Considering the spatial distribution of magnetic field strength and induced current density, the wide rectangular section in the figure is composed of different orange rectangular sections. Based on the electromagnetic field theory and finite Fourier method, the analytical equation of reluctance, magneticness, and hysteresis can be calculated. In consequence, the core loss can also be calculated. For differences from other magnetic circular theories and more details, please refer to our papers and 5-page reports. The third section is about application methods related to the competition. Start with data. First, reference one has identified various factors that influence magnetic core loss, including material size, frequency, excitation type, and so on. Second, the material manufacturers provide limited data. The data sheet is more about changing trends, not precise values. Third, unfortunately, the final test only has data on frequency, temperature, magnetic flux density, and magnetic field strength, but there is no data on material size, conductivity, etc. Our analytical model requires more parameters to calculate the magnetic circuit components. Therefore, we can only obtain the final result through fitting based on the results derived from our theory. Based on the first equation, our final test is fitted using the second equation. Thereby, the corresponding magnetictance and hysteresis components can be calculated. We compared the losses at different frequencies and of the two preliminary materials, 3,6 and N87, at a specific magnetic density, amplitude, and sinusoidal excitation at 25 Celsius. It can be seen from the figure that the overall error is within an acceptable range. Saturation has long been a significant source of nonlinearity in magnetic circuit. When exposed to high frequency and high magnetic flux density, local saturation can occur within the magnetic core. Figure 1 is from a reference 2. It can be seen that the magnetic field distribution in the core is very uneven. It is difficult to take this phenomena into account when calculating the overall loss only through Stanley's equation-based methods. This uneven phenomena may be related to the size of the material, conductivity, and other parameters, which were not provided in the final test. Our study addresses this issue by utilizing finite polynomials to fit changes in the eddy current coefficient and hysteresis coefficient with magnetic density amplitude. In practical applications with high frequencies, pulse-wise modulation waves usually cause magnetic flux density waveforms to be triangular trapezoidal waves. Previously, we obtained parameters under sinusoidal excitations at varying frequencies and magnetic densities. Now, to solve the problem of arbitrary excitation, we combined Fourier decomposition. Here we still use 3,6 and N87 as examples from the error distribution histogram. We can see that based on our model, the error of N87 is much larger than that of 3,6. According to the material manual, the most significant difference between these two materials is their conductivity, which varies by 100 times. This situation also happened in the final test. The conductivity of material B must be relatively large. Therefore, our model can achieve relatively good accuracy with a relatively small size. So while materials with low conductivity have large errors, these are two triangle waves with different duty cycle. The loss of material N87 under the excitation of a triangular wave with 80% duty cycle is 4 times that of 60%. As explained in the reference 1, the hysteresis loss is caused by rotational friction of magnetic domains. This means that the faster the rotation speed of a domain is, the greater the hysteresis loss is. Verified by a large amount of computation data, we found that Fourier decomposition is not accurate enough in predicting core loss, which caused by large derivative of B vs T. in materials with a large proportion of hysteresis loss. So there is room for improvement in the accuracy of our current prediction model. Okay, referring to the organizer's email, we draw the following conclusion. First, what we learned? We learned lots of valuable content, and it was undoubtedly a long but interesting competition. A large amount of data from the competition allowed us to discover core loss is affected by many nonlinear factors. Different influencing factors will introduce different parameters. The sufficient experimental data are necessary. In the final test, the amount of data for material D is very limited, so most of the team's models were not very accurate. Second, what has been done? The vector magnetic circle theory equates eddy current loss and hysteresis loss to McDuckens and hysteresis components with a clear concept and a simple model. In addition, our analytical model is beneficial to consider nonlinear factors such as size and situation, etc. Our fitting method based on the results of our theory can use a smaller model to obtain a more accurate prediction data for materials with relatively large conductivity. Third, what to be done? Quantitatively characterizing more nonlinear factors into our model is what we need to do next. That's all. Thank you for your attention and listening. And special thanks to the organizers of MagNet Challenge and my co-authors.
Thank you, Chenbo. Very nice model, and especially when I compare your model and Mondragon model, one is sort of from data towards physics, the other is sort of bottom up from physics all the way going up to data. So very interesting. When we were evaluating your model, we had a question of, because we noticed you use different number parameters for different material. So how was that decision made, and how do you reach the particular choice of number parameters for each material? Do you hear my question? Sorry.
Yes. Our current model only considers frequency, temperature, magnetic density, and excitation type, and uses the Fourier decomposition method to deal with non-sinusoidal waves uniformly, without distinguish between triangular waves and trapezoidal waves. We also tried to use a power function to represent it, but found that it is difficult for the power function to fit the nonlinear phenomena caused by the magnetic density in a wide range. Using finite polynomials avoid these problems. The parameters in the model or code we currently submit are more accurate parameters after training. The training process is not shown in the code. Since our current model works better for materials with sufficient data and relatively high conductivity, I think we can semi-automatically generate a more accurate and compact model for this part of the material.
Okay, so you're saying there are some human decision process in the middle when you are choosing a model or sizing them, like how many parameters you need for each material. Is that sort of like a true understanding? So there are some sort of, we feel this material needs more parameter and we feel the other material needs less parameter, and that's why you have different number of parameters for different material.
Actually, actually, our model needs 8 parameters.
You need 8 parameters.
Yes.
But in the end, the inference model you submitted has more parameters than 8, way more. I think, what was the number? I forgot. More than 60. Like, you guys are slightly larger than Mondragon model, I think.
Yes, because our theory has just begun, we cannot yet quantitatively characterizing many nonlinear factors, and we hope
Mhm.
every parameters in our model must have a clear physical explanation.
Mhm. So how about temperature? Like, how do you factor temperature into a physics-based model? Or you have to train a set of parameter for every temperature?
Train a set of parameters for every temperature.
Okay, so that's the solution now. So for temperature, there's no way of considering that in the equation. It has to be temperature by temperature.
Yes, yes.
Okay, okay, great. Yeah, very nice. Again, well, thanks for trying analytical model. It's hard and it's really hard to get an accuracy like you guys are presenting. So that definitely represent a lot of work, and novelty. Haran and Shukai, any question from the audience?
I have a quick comment. I think for this challenge, we did not really include the effect of geometry. I believe only one material really was an E-core. All the other ones are toroidal. But I think you guys may actually do pretty well if we were to add a factor when it considers the effect of geometries, since you guys actually do factor in the geometric effect, which I think is going to fare pretty well for you guys. Let's say if we throw in different geometries, and I think for industry applications, that's very important as well as academic. So I think that's a very good plus factor that is not really part of this challenge, but I think that's something to be applauded for. So
Yeah, that's very nice.
Yeah,
Yes.
if given the specific geometry shape, conductivity, and permeability of magnetic circuit, we can use our analytical loss model. The reluctance, magnetictance, and hysteresis components can be calculated. If that, I think our accuracy will better.
Yeah. So yeah, also as I said, like this competition is not